We good?
Oh my goodness. Wow, who let me be session chair? This is a terrible idea. Okay, next up we have Dominik Klumpp talking about commutativity and concurrent programs. Please take it away, Dominik.
Okay, thank you for the introduction and welcome everyone to my talk. I'm a PhD student at the University of Freiburg and I'm presenting joint work with Azadeh Farzan from Toronto and my advisor Andreas Podelski. So let me start by just explaining a bit what this commutativity business is all about. We want to verify concurrent programs such as this one. So we have here two threads. They communicate, in this case, via shared variables. And we look at this under sequential consistency. So it's a bit different from the last two talks. And a specification is given where if certain variables are initialized to 0, in the end, the variables x and y will be equal. In this case, that's hopefully relatively easy to see. Both threads sum up the first n elements of some array, and therefore the results in the end should be the same. Now, if we want to algorithmically verify this, one approach would be to draw this control flow graph that corresponds to a naive sequentialization, right? So for every interleaving of the two threads, we have every interleaving of the two threads can be found in this control flow graph. And we could try and just verify this like we would for any sequential program. But it turns out that's not a good idea. As you might have guessed, this control flow graph grows exponentially. And we also need often rather complicated invariants to prove this program is correct. So here, some unbounded sums over array elements. Such invariants are often difficult to find for algorithmic verification. So that's where the commutativity can help us. We observe that for many statements of different threads, the order in which they are executed does not matter. So for instance, here, whether I first increment x by a of I and then y by a of j or vice versa, the result will be the same. And therefore we say that these statements commute and sequences of statements or program interleavings that only differ in the order of such commuting statements can be considered equivalent. The key idea here is that if I prove that one trace is correct, I know that all equivalent traces are also correct. And therefore, it's sufficient to verify only a reduction of the program. A reduction here is a subset of the program interleavings that has at least one representative for each equivalence class. So instead of verifying this complicated program, I can verify this program. Every interleaving from before is equivalent to one of these. And as you can already see, the automaton or the control flow graph is smaller. And we also find that often the invariants become much simpler. So here our post condition x equals y is actually an invariant. And we just need some information on the loop counters to make it inductive. So to algorithmically verify this, we would iteratively construct a Floyd-Hore-style proof. So just imagine that we annotate the locations of this reduction with invariants for each location. If we would want to cover all interleavings, we often need complex proofs, both qualitatively, as we saw in the example, something quantified, nonlinear, etc., but also just we need many different assertions, and that can be a problem. Whereas a reduction often has a much simpler proof. And the second problem is that if we want to check if some proof that we have actually covers all interleavings, we need to look at all of these many different locations, and that costs an exponential time, whereas a reduction can often be represented much more compactly. So let's look at these reductions a bit more closely. As I said, it's a subset of program traces with one representative for each of these equivalence classes defined by commutativity. So it's defined by 3 parameters, a program to be verified, which tells us which program traces actually exist. Then we need to pick for each equivalence class one representative, and we use here this formalism of a preference order. If you're interested in that, you can take a look at our POPL'23 paper. The star of today, however, is the commutativity relation. That's a binary relation on statements, which tells us which statements commute and thereby defines the equivalence classes. Now, by the fact that I write this here as a parameter to the reduction, you can already see there is more than one choice of this. And that's actually one of the key points in our paper that we want to reinforce. There is a wide spectrum of possible commutativity relations that you could use for this kind of verification. So I'm going to preview quickly the 3 main points that the paper covers and that I will talk about today, and then we go into more detail. The first one is related to what I just said, right? There's a large space of commutativity relations, and we define in the paper a framework for safe abstract commutativity relations. So safe means there is a condition that we define which ensures soundness of the resulting verification. And in our framework, relations are constructed such that they are safe by construction using abstractions. We will see how that works in a moment. But these abstractions, they're always driven by the proof that our verification is constructing. Secondly, once we see that there are actually many possible commutativity relations, we would have to make a choice. Which one do we use for our verification? But these relations can be very different and can have incomparable strength. So what we introduce as a second contribution is what we call stratified commutativity, a new proof rule that allows us to combine multiple commutativity relations in one verification. And we believe, and we are very thankful to one reviewer who also pointed this out, that this is actually applicable in many settings, not just algorithmic verification. It could also be useful in some kind of deductive or semi-interactive verification. And it is strong enough to subsume the corresponding proof rules for each individual commutativity relations, which means one doesn't have to choose a commutativity relation, you can just combine them. To make that amenable for algorithmic verification, we need a slight variation, right? If we want to apply this in an algorithmic setting, we specialize the rules such that all of the premises of the proof rule are either true by construction or decidable. And in particular, we give a new decision algorithm for the key premise that is based on principles from partial order reduction. So now, let us start with the first point, safe commutativity through abstraction. The question here is, what does it mean that 2 statements commute? Well, I said before, the order in which they are executed does not matter. If we want to formalize this, one notion could be the statement, the sequence statement 1, statement 2 behaves exactly like the reverse sequence, and formally some semantics of this sequence is equal to the semantics of statement 2, statement 1. This really means the order of execution does not matter for all programs and with respect to all properties. No matter, or at least all safety properties, no matter what we're going to verify, this works. So it's very general. It's a very general notion of commutativity. But because it's so general, it's also limited. If we focus on a particular program and a particular property, we can actually get more and different kinds of commutativity than what this definition would allow. So we focus on a given program and property, and then we only ask that the 2 sequences of statements behave similarly enough for this program and property. We abstract away from certain details that are irrelevant to this property, while of course making sure that we preserve those details that are relevant in order to maintain soundness of our verification. And a key insight here is that to judge what is relevant and what is irrelevant, we can use the partial proof that our verification constructs or has constructed at a certain time. So let's see how this works in detail. We take a proof, and for now we can just imagine this as a set of valid Hall triples that our verification has found. To conclude that a program is correct, we compute a reduction, and we check whether all the traces in the reduction are proven correct by this proof. If that is the case, then P is correct. But this doesn't hold for any arbitrary commutativity relation that you could make up. To make this actually sound, we need a second premise, namely that this commutativity relation is what we call safe with respect to the proof. Which means that traces that we have already proven correct cannot be equivalent to incorrect traces, they must be only equivalent to correct traces. And it's crucial that this safety really depends on the proofs, because that is only the only thing that allows us to get more commutativity than in the setting where we demand that the two orders have exactly the same semantics. It is still a special case, right? If we define commutativity based on the concrete semantics, that is safe with respect to all proofs. But the question for us now is, how can we get safe commutativity for a particular given proof? And we see one way to achieve that is through what we call safe abstraction. We take a statement abstraction, so that's a function alpha that maps statements to more abstract statements that allow more behaviors. And then we can simply define that under this abstraction, two statements commute. If we take their abstractions, we execute them in either order, we should have the same semantics for the two orders. So basically just reducing it to this original notion of commutativity, but with the abstraction in between. And then we show that if this abstraction, the statement abstraction, satisfies two simple properties, then we can conclude that the commutativity is safe with respect to the proof. The first property simply states that it is indeed an abstraction. All the behaviors of the original statement are also allowed under the abstracted statement. And the second, the preservation, is where the proof comes in. For all Hall triples in our proof pi, they are still valid if we replace the statement by its abstraction. So let's see an instance of that. One instance that we show in the paper is called projection to the proof. And the idea is simply if some variable x is not mentioned in any assertion of the proof, we can ignore x when we determine commutativity. We do this through an abstraction, where whenever a statement reads such an irrelevant variable x, we replace this with a read of a non-deterministic value. And also, whenever it assigns something to such an irrelevant variable x, we make this a non-deterministic assignment of x, or header. So for instance, if our proof contains only the simple Hall triple, true, then y gets x plus x. Afterwards, y cannot be 1 if these are integers. Then the abstraction would replace this x by some non-deterministic value. So in effect, it is just an assignment of some non-deterministic even value to y, right? It must still be even, but it need not be 2 times x. And the abstraction of some assignment x gets 0 is just assign some non-deterministic value to x. Now, if you look at these two statements, originally they would not commute because the order in which you execute them matters. In one case, y is always 0, in the other case, y might be different. But their abstractions commute because the first abstraction is only concerned with y, the second abstraction is only concerned with x. It doesn't matter in which order we execute these two. So this is one case where projection to the proof gives us additional commutativity. We show that this is always safe by showing that it satisfies abstraction and preservation, these two conditions. And we also have an empirical evaluation in the paper, which shows that it can significantly improve verification, especially if we look at lightweight properties like memory safety, where there are typically many variables that are not relevant and can be abstracted away. I'm not going to go into too much detail here, but you can find the statistics in the paper. So there are some advantages. We often get additional commutativity. It's a very easy, simple abstraction that we can define and compute easily. But yeah, how else would it be? We also have some limitations. First, we show that there are cases in which we are just bound to lose commutativity with this abstraction. And even if that's not the case, the way we implement this abstraction with non-deterministic value introduces quantifiers in our verification, and that is just a huge practical obstacle to the verification algorithm. So we have here an instance of the general principle that abstraction doesn't always improve the commutativity. In fact, the abstract commutativity and concrete commutativity are often incomparable, and thus our approach is to combine the two. That brings us to stratified commutativity, the proof rule that allows us to combine relations. Before we get to that, well, the first idea you might have is, well, if you want to combine two relations, why not take the union? However, it turns out that even if both commutativity relations individually are safe, the union is often unsafe. I'm not going to go through the example here for time reasons, but you can find it in the paper. And the key takeaway from this for us was that it really matters in which order you apply the commutativity relations. If you take the union, you can swap some statements up to concrete commutativity, then swap some statements up to abstract, and then go back to concrete and back and forth. And this is really where the unsoundness stems from. So what our stratified commutativity does is to sequentially combine the relations. So we take any trace tau1 that has been proven correct. If we swap certain statements up to the abstract commutativity until we reach some trace tau2, and then we decide to switch from the abstract to the concrete commutativity. So now we take statements in tau2 and we swap them up to the concrete commutativity until we reach some trace tau3. In this case, we can then conclude that tau3 is still correct because it's connected through these two equivalences to a proven trace. If we swap here abstract and concrete, we do first concrete and abstract, this breaks down. So it's really crucial that you maintain this order. And this is really what our proof rule says, is if every trace of the program, every trace tau3 essentially, must have some tau1 and tau2 such that tau1 is proven by our proof pi, and they are connected through these two equivalence relations. This is here given in a slightly different notation where the closure of some set of traces is the set of all equivalent traces. And we have an inclusion that P is included in this double closure. Of course, we also have still the side condition that this abstract commutativity must be safe. If this is the case, then we can conclude that P is correct. And this is our general proof rule. Well, it's not so general yet. We can generalize it even more. It doesn't have to be two commutativity relations. You can have any number of commutativity relations, I1 to IN, as long as all of them are safe and satisfy a side condition that we call stratifiability. You can intuitively just think of this as I1 is more abstract than I2 is more abstract than I3, and so on. The formal definition of that can also be found in the paper. And the last point is decidability. So here I'm just going to compare quickly how it is for one relation and in the case of stratified commutativity with multiple relations. The corresponding question for one relation would be this one, right? We check if P is included in the closure of the proof, or equivalently, is there any reduction of P that is covered by the proof? And this is a question that's known to be undecidable, even if P and this proof pi are represented by regular languages. And it doesn't become any more decidable if we add a bunch of other commutativity relations. The key problem here is that we have to select the right representative for each of the infinitely many equivalence classes, and that's just not always possible. In the stratified case, we even have an additional challenge that we need to select the proper sequencing. So we have to choose when we switch from one relation to the next, and knowing that we cannot switch back. So to make this decidable, we introduce this kind of preference order that I briefly mentioned before. So this is a lexicographic order on the traces, and our proof rule now demands not only that tau1 and tau3 are connected through these equivalence relations, but also that tau1 is less or equal in this order to tau2 is less or equal than tau3. If you're familiar with trace theory, we are essentially extending here the idea of lexicographic normal forms. This then results in a new proof rule, right? So what this preference order does is just, it tells us how to select representatives. We fix one selection of representatives. We get one particular reduction rather than checking for the existence of a reduction. And now we get a proof rule where this premise is decidable. We present in the paper a partial order reduction algorithm that can decide this precisely. And again, this can be generalized to n relations with the same side conditions as before. Also, our algorithm also covers the case of any number of relations. So with that, I conclude. I've briefly reintroduced the fact that commutativity-based reductions can help us simplify proofs and check proofs more efficiently. And one key aspect here is the commutativity relation. We've seen that there's a large spectrum that can be automatically computed in a way that they are safe with respect to the proof through safe abstraction. Because they are incomparable, we've introduced stratified commutativity to combine multiple commutativity relations, and we've introduced a decidable variant for algorithmic verification. With that, I am finished, and thank you for your attention, and I'd be happy to answer your questions.
Thank you, Dominik. We have time for one quick question. Sorry for the shortening due to technical issues. Question from the audience? Okay, I have a quick question. One thing that wasn't clear to me from the talk is what is the logic you're working in for sort of what these proof properties are in? Because to be deriving things from the property, you need to sort of know what the property can express. And sort of, I'm wondering sort of what is the one you're using in this setting, and then how general do you think you could make it?
So the assertions that make up our proof, is that what you're asking for? Or?
So when you're talking about proof and doing this sort of property-specific commutativity relation definition, that property is written in some logic, and it wasn't clear to me which. Sort of what are the expressible properties, and how can you do quantifiers? Is it just sort of strictly sort of propositional logic over program variables? Something else? Just wondering what the logic here is and how we might generalize it.
So we look typically either at precondition, postcondition pairs or assertions in the program. And the assertions or the preconditions, postconditions are some first order logic over the program variables. If you have quantifiers, it will work in principle, but the algorithmic part will probably struggle with that.
Okay, got it. Thank you. People can contact the authors for more questions, maybe talk asynchronously online. Let's thank Dominik one more time and go get lunch.
Thank you.
All right, I believe lunch is simply out there. Welcome to POPL'.